Hi everyone, this is your week 12, day 23 lecture video from Professor Iris Miano. This is Santa Monica College Math 32, otherwise known as Plane Geometry, and we are heading into the last unit of this course. We are going to cover these two sections in Chapter 9. They're the only two sections in Chapter 9 that we'll cover, and they concern circles and all of these related items. So we will, just a moment. Okay, sorry for the interruption there. I just had to check something really quickly before we got too deep into our discussion. Now, in these two sections, a healthy amount of terminology is going to be introduced, so just, stick with me as far as being able to keep up with all of the new verbiage that's coming your way. And there's also a lot of opportunities for you to draw some really pretty pictures, and some of them are going to be involving circles. A lot of the circles that you'll be working with will already be provided for you on your lecture notes, but if you are ever asked to draw a circle, I highly recommend that you pick back up your compass in order to make some really pretty and highly accurate looking circles. This is not necessary, and you will not be asked to use your compass in any kind of official capacity for the rest of the semester, with the exception of the final exam. Of course, for the final exam there will be a construction on there, so definitely make sure that when the final exam rolls around that you still know how to do any of the constructions that have been presented so far in this course. Okay, let's go ahead and get started on the terminology that we need to get a handle on. So the first thing that we need to define is what a circle is. It's the set of all points on a plane that are at a fixed distance from a given point known as the center of the circle. So in the space provided underneath this definition, you can draw yourself a circle. Again, I recommend that you use your compass to make it look really pretty. And the center of the circle is just some dot in the middle of it, and it has usually a name to it, and that names the circle itself. So for example, this is circle Q, and we'll get to the example in just a moment. First, let's also define what a radius is. It's a segment that joins the center of the circle to a point on the circle. The plural form of radius is radii. Now, in this one figure, we have both the circle, which was originally just this bit, with a dot in the middle representing the center, and also named Q, which names the circle as well. And then when we introduced the radius, we drew a line segment from that center Q to a point on the circle called P. So herein lies the examples that we can put down also underneath each defined term. And this will allow us to introduce some symbology. Okay, so when you want to write a circle with its name next to it, if you want to write down a named circle, you do so with this symbol, the circle with the dot inside, and this represents mathematical shorthand for the word circle, and this reads as circle Q. Okay. Next down here, if we want to, for example, name a radius according to the figure that we have here, and notice in your lecture notes there's an additional space underneath the defined term radius, and I recommend that you draw yourself another circle also called Q with the center point Q, and then draw your point P on the circle itself and draw a straight line connecting the two as your example radius QP, which we would name the same way we would name any line segment with this straight line trajectory hat on top. QP is indeed a radius. Okay? Cool. So even though we're going to continue to use the same figure for some subsequently defined terms, I recommend that you redraw them each time. But these lecture notes are completely up to you, how you use them and what you want to add to them. So let's continue defining some more terms. For instance, let's define what a chord is. A chord is a line segment that joins 2 points on a circle. Okay, so that can be either RP is a chord, SP is also a chord, but it's a special kind of chord called a diameter. A diameter is a chord that contains the center. So now, underneath each of these defined terms, we can redraw this figure, or just draw it once and refer to a chord. Could be RP, right? Or you could call SP a chord as well, but since it goes through the diameter, it usually gets through the center, it gets the special designation of being called a diameter. So in this case, the best example of a diameter is this SP line segment, and the most intuitive, I guess, example of a chord, just a generic one that goes along with this definition, would be RP in this case, the case of this figure, I guess I would say. Okay, but to be clear, diameters are chords themselves, because a diameter is, it fits the definition, it is a line segment that joins 2 points on a circle. It just happens to encompass the center, so it gets this designation. Okay, moving on. Congruent circles. Congruent circles are defined as circles that have congruent radii. So please note circles T and Q presented here and also on your lecture notes. And so draw yourself a radius in each one of those circles. And you can call the radius on circle Q TU. And let's say we drew another radius also on a circle Q and called it QP. So if they're both 4 centimeters long, then that means that these two circles are said to be congruent to each other. That's it. If you want to say that circles are congruent, you need only show that their radii are congruent. Okay? Cool. And if their radii have the same measure, then they are congruent to each other. Radii are simply line segments, right? So all of the things that you know to be true about line segments are also true about radii, which are just a specific kind of line segment that joins a circle's center to its outer edge. Great. Moving on. Concentric circles are coplanar circles, so they just mean they lie on the same plane, same piece of paper, same surface, that have the same center. Concentric means same center, right? So it's all in the name. So here, let's entertain some circle K, or some circle, some point K, and then put a couple of circles that are positioned in such a way that K is the center for both of them. So then this is what we would call two concentric circles. They're both have the name K. You would call the larger one, or the outer circle K, inner circle K, if you like. Although the book does not make any distinction on how you would name these two separate circles. They just call them concentric circles with the same center K. All right, moving on. Okay, so for the next 4 terms here, we're going to use the same figure that's already present in your lecture notes, but what I'm going to do in the video itself is anytime I'm defining a particular item, I'm going to highlight it with a red color. So to start things off, an arc, just a generic arc, it's very much plainly defined as part of an edge of a circle. So RP, this highlighted red bit from R to P that's curved, right? It's the part of the circle's outer edge, is considered an arc. Now there are particular types of arcs depending on how much of the circle you are illuminating. And so a semicircle is going to be if you are illuminating exactly half of the circle, and the way you know you're illuminating exactly half is that the endpoints make up a diameter. So notice diameter PS, and I know it's a diameter because it encompasses the center Q. By definition, it has to be a diameter. If I take the arc from P to S, then I know I'm taking up exactly half of the circle, and the technical term for this is semicircle. Okay? Now, sometimes you're going to have arcs that are relatively short, so they illuminate less than half of the circle, and that's going to be called a minor arc. And if you illuminate more than half of a circle, then you are showing a major arc. So I have some examples of both. For instance, before I move on, let me first give you an example of a semicircle that's going to be arc PS. And I want to highlight something for you that was a technical component as far as making this PowerPoint is concerned. Notice the hat that's going on here, right? I have a hat and it looks like it's kind of pointed. It's meant to be smoother. So if you're looking at the notation that's in the textbook, it looks more like this. PS, and it's got like a smooth arc to it. Now that's what you want to be actually writing down when you are practicing this stuff. This hat with a little bit of a point to it is the closest thing that I could get notationally for naming arcs. So this is arc PS, that's how you would read this, okay? And it's meant to be looking like this. So I'm just drawing a little bit on top. Okay. Now, so as we go, you'll see these kind of slightly pointed hats, but they are meant to be smooth curve hats, and that's supposed to be designating the name of the arc. Now here is an example of a minor arc. Now that was the generic arc RP that was presented earlier, and this is how you would name it. This is an arc RP, and remember, try and envision this as being a smoother curved hat, okay, on top of RP. Whereas a major arc would be the remaining bit of this circle, and it still has endpoints at R and P, but it encompasses another point S. So anytime the arc that you are trying to capture here has an additional point to it, it's always good to have that be part of the arc's name to distinguish it from the other type of arc that could have that same endpoint, okay? So for this major arc, you would name this arc RSP. Does that make sense? You want to name the points in the order in which you see them, and you could go the reverse order, but S has to be in the middle. So for instance, this arc could also be called arc PSR, if you like. Okay, but that's the difference between a minor arc and a major arc. A minor arc is an arc shorter than a semicircle. A major arc is an arc that's longer than a semicircle, but it's shorter than the entire circle. Okay, which RSP definitely captures that definition in its arc. Okay, great. Moving right along. More things to define, so many things to define. So yes, if you ever need to, in the midst of this video, take a pause, come back to it, I don't blame you. There's a lot of content here. But let's continue. A central angle of a circle is an angle whose vertex is the center and whose sides are radii. So for instance, in this figure here, which may or may not be in your lecture notes, if you ever find that a figure is not in your lecture notes, it's your invitation to draw it. And remember, if you want to make really pretty circles, please use your compass. But in any event, what do we have here as the central angle? So angle RQP, therefore, would be the example associated with this figure. And the intercepted arc is going to be the part of the circle that is captured by the endpoints of that corresponding central angle. So for instance, RP would be the intercepted arc by angle RQP, central angle RQP if you like. You could just call it angle RQP though, but it happens to be a central angle because it is its vertex is at the center and its sides are radii. Okay? Moving on. Oh, we have a postulate in our midst. In a circle, the degree measurement of a central angle is equal to the degree measurement of its intercepted arc. Yes, so arcs have measure and angles, of course, have measure. We already knew this. So let's entertain a quick example to illustrate postulate 16, noting this figure right here. If the measure of the central angle RQP is 65 degrees, then what is the measure of arc RP? Yes, so we're going to use the same lowercase m as the little prefix to say measure of, and then arc RP is going to have its measure, and what will it be? Well, it'll be the same measure as the central angle that it encompasses, okay? Great. So that's the relationship between central angles and intercepted arcs. Then we're going to talk about inscribed angles a little later and their relationship to their arcs. But for now, let's go ahead and tackle the very first theorem in this section. It states that a radius that is perpendicular to a chord bisects the chord. Okay, so the radius in question is radius QS, and notice how it is indeed perpendicular to chord RP. Okay, and the reason I know that is because a right angle has been formed at the intersection. Okay, so that means that RP has been bisected at point T. So RT is therefore equal in measure to TP and therefore congruent. So here we go. We have QS is perpendicular to RP. That's like the preamble. So therefore, RT is congruent to TP. And here are some tick marks, some familiar notation to indicate that those two line segments are indeed congruent. Okay, great. Now, here we go. Here's some more terminology. In a circle, or congruent circles, which is what we have here, or that's the implication. Congruent arcs are arcs with equal measures. So, given that the two circles T and Q, let's assume that they're congruent to each other. So by definition, if you recall, that means that their radii are congruent. So if the radii are congruent, right, then and let's say that the arcs are congruent as well. VU is congruent to RP, and that's these arcs right here that are formed at the endpoints of the central angles formed. Then the measures are equal. So this isn't saying anything super spectacular right here. This is just relating the definition of congruency to being equal in measure and extending it to arcs. That's all that this is saying right here, okay? And of course the converse is true. That's always going to be the case for any defined terms, right? So if you are starting off with arcs being equal in measure, then you could say that they're congruent. That's what is meant to say that the converse is true. Okay, moving on. Postulate 17. If arc AB and arc BC only intersect at point B, then the measure of arc AB plus the measure of arc BC equals the measure of arc ABC. Does this sound familiar? It's the arc addition postulate, basically. And we want to make this distinction of calling arc ABC using that B in the middle because it contains point B, right? Whereas if we just called this arc AC, we would be referring to the major arc. Does everyone see the distinction? The major arc with endpoints A and C, arc AC, is a major arc, whereas arc ABC is a minor arc. Hopefully everyone can see the distinction there. It's very important to catch that nuanced detail with the notation. Okay, cool. So basically this postulate is the arc addition postulate. Okay, like the segment addition postulate and like the angle addition postulate. All right, now we're describing, or we're going to be defining an inscribed angle of a circle is one whose vertex is a point on the circle and whose sides are chords. So here's an example of what an inscribed angle looks like. Okay, so this would be angle RSP, if you like. Or we could just call it angle S if we want to, which is what I've done in my notes. So angle S is an inscribed angle in circle Q. Now, next, we're going to have a theorem that describes the relationship between inscribed angles and their intercepted arc. And the relationship is that the inscribed angle is exactly half of the measure of its intercepted arc. So let's say for the sake of this example that the measure of arc RP in the figure here was 50 degrees, then what do you suppose would be the measure of the intercepted arc? It would be 25 degrees, as you can see in the blue here, okay? It's exactly half of the measure of its intercepted arc. So that's going to come in handy, definitely, when we get into some examples later on in the section and in the next section. Moving on, 913. In a circle or congruent circles, as you see pictured here, congruent minor arcs have congruent central angles, okay? So considering that these two circles T and Q are congruent, if the arcs are congruent, arcs VU and RP, that is, like the arcs that you see here that you would call minor arcs, right? VU and RP. If they're congruent, then that means the central angles, angle VTU, has to be congruent to angle RQP, because there's a relationship between intercepted arcs and central angles. So if the intercepted arc and central angles are congruent, if the intercepted arcs between two congruent triangles are congruent, then so must be the two central angles among the two congruent circles. Okay, cool. There's more. Now, let's say that we wanted to go the reverse direction with it. Let's say we had two congruent circles and that their central angles are congruent. Well, then that would mean that you would be able to conclude that their intercepted arcs are therefore congruent among the two triangles as well. Okay? Cool. So that's basically the converse of the 9.1.3 theorem that was just presented. Okay? All right, 915. In a circle or in congruent circles. So for this illustration, I decided to just use a single circle. If we have congruent chords, then they have congruent minor and major arcs. So the illustration goes as follows. Assume in circle A that chords B, C, and D, E are congruent to each other. Therefore, arcs B, C, and D, E, the intercepted arcs according to those chords, have to be congruent to each other as well. You can also say this about arc BEDC, comparing that to arc DCBE. A little bit of a challenge there for you guys to visualize that. Maybe go over with your finger or your writing utensil to follow that. So that is to say that using the same theorem, you could conclude that arc BEDC is congruent to arc EBCD. Those are the major arcs associated with those two chords that are congruent. Okay, cool. Next one. Basically, it's the converse. Now, let's say that we had congruent arcs, and then let's say, for the sake of argument, they were B, C, and D, E arcs, and if they're congruent within a circle, then the chords that make their endpoints have to also be congruent as well. The converse of the previous theorem. Okay, moving on. There's so many here. And a lot of them have a converse counterpart to them. And I believe this theorem is no different. So the next one after this, I believe, will be the converse. But here it is. Chords that are at the same distance from the center of the circle are congruent. So what's being said here in regard to this figure is that if AG, that's the length of, or the measure of the line segment from the center to a point on chord BC, and another point on chord DE, so those are points G and F respectively. If those measures are equal, then the chords themselves must be congruent to each other. Okay, and though the converse is also true, that is to say that if the chords are congruent to each other within a circle, then the distances between them must be equal as well. All right. Great. We're going through these pretty fast, so I hope you're picking up what I'm throwing down. But if at any point we're going through this in the lecture video and you're like, ooh, I would like a little bit more on that, maybe another example or some such thing, then I'm happy to go over that more in class. But for the time being, let's go ahead and continue. This one's pretty special. It actually doesn't have a converse counterpart, but it does have a little bit of a link that I'm going to press in just a moment to have an illustration of this. So this says an angle inscribed in a semicircle is a right angle. So let's say you have a semicircle, or this could be even a complete circle. If we had the rest of the circle, like another semicircle going from A to B on the other side, then D would be the center and AB would be a diameter, all that business. And if we had these two chords connected in this point C, well then it would have to form a right angle. Now you might be wondering, well, is this true no matter the position of C? Yes it is, and I'm going to show you this link right here. Look at that. Can you guys see that? So I'm not sure what this Pinocchio is all about. Oh, we have advertisements for some kind of bathroom cleaner. Fun. Okay, so just try and ignore that as best you can. So it says drag any orange dot. So drag the orange dot and put it over here, right? Look, notice that the angle that's inscribed is still a right angle, isn't it? What if we went all the way down, like as close as we could to A, like without actually touching it? Still a right angle. Isn't that phenomenal? So it doesn't matter where you are positioning this point, right? That makes the right angle vertex on your triangle that's inscribed here. It's always going to be a right triangle. Isn't that cool? Okay, so we would just basically say that no matter the position of, what would it be? Go back to here. This particular C point, the right angle vertex of the right triangle that's inscribed, it's always going to be a right angle no matter what. That will never change. So I believe there's an extra question on your lecture notes like, oh, you know, what can we say definitively about the position of C? Like, it's never going to not make a right angle right here, is my point. Okay? Cool. Moving on. Next, 10th theorem in succession here. If two inscribed angles intercept the same arc, then these angles are congruent. This is actually going to come up a lot in the examples that you undertake in this section and the next. And so, for example here, I want you to consider angles BCE, BCE, that's this angle right here, and angle BDE, BDE, okay, this angle here. So notice that when you're thinking about these as inscribed angles in the circle, they both intercept the same arc BE that's lit up in blue here. So that means that they have to be congruent to each other. That's the purpose of this theorem here, okay? And then of course, oh no, there's no converse counterpart here. Okay, but we are ready to write a paragraph proof as the example exercise, like the encompassing exercise for this one here. Here is a chance for me to reiterate that paragraph proofs, okay, are not, unless specifically instructed, going to be using the indirect method. Okay, now there's no mention of the indirect method here, harkening back to section 4.2, okay? However, indirect method proofs are always written in paragraph form, but this is a paragraph proof, which is going to be just telling a story, okay? Regardless of if you're writing a paragraph proof or a chart style proof, you always start with the given information and you reason your way down all the way to the proof statement. You have to justify every statement along the way, just like you would in a chart style proof, but you're going to do it writing full English language sentences. I tend to write run-on sentences myself, so I'm definitely not going to be very harsh on any kind of grammar instruction or grading. So yeah, if you tend to write run-on sentences as well, I'm not going to be very stringent about that at all, because I would probably write it about the same way. Okay, so that being said, let's look very carefully at what's given and look at the figure and then try and prove triangles, what is it, RST is congruent to VTS triangle. Okay, and we're given that RS and TV are diameters of circle W, and that's it. Okay, so we're going to have to draw a lot from the figure, really, in order to move forward with this proof. So I invite you to just write down this paragraph proof word for word according to my example. And, you know, if you want to subsequently from that think about how you might slightly reword it, I think that's a valuable exercise as well. But here we go. I'm going to start with addressing the given information and drawing a conclusion there. Since RS and TV are diameters, they must be a pair of congruent line segments, okay? All diameters within a single circle are congruent to each other by definition, okay? So that's how I am justifying that those two line segments are congruent. And I'm not going to add any notation to it, just because where would I put the tick mark? I would probably put it directly on W. It wouldn't really show up. If I put it here or here, then it might seem like these aligned segments in a response to the placement of this W point are congruent to each other, and that's not what I'm trying to say. So this figure does not lend itself to adding notation to the fact that these two line segments are congruent, just to be clear. Okay, next, I will claim that angles R and V are congruent to each other because, if you notice, now we could also call this angle TRS and angle SVT if you like, but I went ahead and used the one letter term or one letter name for these angles just as a stylistic choice. So I'm talking about this angle and this angle here. They're congruent to each other because they are inscribed angles that intercept the same arc, TS. And inscribed angles that intercept the same arc, as we just saw in a recently presented theorem, are indeed congruent to each other. Okay, so far among these two triangles, I have 2 lines, 2 angles. I need either another set of lines that the angle is like between, or I need another set of angles. So let's see what I come up with here. Looks like I link together line segments RT and VS. Think about this. How can I say that they are congruent to each other? Well, this next one as justification is quite the run-on. Okay, I get to claim that these 2 line segments are congruent because angles RWT and VWS, they're both central angles, right? But also they're congruent angles because they're the result of these 2 diameters intersecting each other, yeah? Okay, so they're congruent vertical angles. Vertical angles are congruent. They're also central angles, and congruent central angles have congruent arcs, and congruent arcs have congruent chords. So basically we were like, these are congruent, which makes these congruent, which makes these congruent. So I went from central angles being congruent because they're vertical angles to that must mean the corresponding arcs that they encompass must be congruent to each other. And then I can draw that into the chords must be congruent to each other as well. They're all connected to each other. So that's how I was able to conclude that RT must be congruent to VS. And then once you put all that together, we have what? Side, angle, side, side, angle, side. So I'm going to be able to say that these 2 triangles are congruent to each other via SAS or side, angle, side. Okay, so that is a wrap, if I'm not mistaken, on 9.1. And so now we're going to enter into 9.2, which is, more angle measures in the circle, more terminology, more. It gets pretty wild. Let's start off with the term tangent, which if you're thinking about trigonometry, the term tangent has its own definition and context there that is different than what we're going to be talking about here. So a tangent in the realm of circles and related items is going to be a line that intersects a circle at exactly one point on that outer edge. This point is called the point of intersection, the point of contact, or point of tangency. So here is a particular line L, and let's just go ahead and nudge it right up against circle Q in such a way that it only makes one point of intersection, point of contact, or point of tangency, and that's going to be the point P that you see here. So notice that I underlined all of those describers in the definition of the word tangent. Okay, great. Now, similarly but distinct from that is a secant line. Now that's going to be a line segment or array that intersects a circle at exactly 2 points. Now this is different than a chord because it goes beyond the circle in either one direction or another. Oh, well, a secant line, I guess, could be also considered a chord if it's just a segment. Truly, that is true. But notice the 2 points of intersection here, P and R, in regard to line L and circle Q. Okay, great. A polygon, this is where it gets really fun because we get to throw polygons in the mix in conjunction with circles. Now the polygon can either be inside of the circle or outside of the circle, and there's different terms for each. So if a polygon is inside of the circle, then it is inscribed in a circle if its vertices are points on the circle and its sides are chords of the circle. Or you could call them secant lines if you want to. Secant line segments, I guess, would be technically correct. But yes, so here polygon or quadrilateral ABCD is said to be inscribed in circle Q. Okay? Yep. And the circle is referred to as being circumscribed about the polygon. Okay, so there's a distinction between inscribed and circumscribed. So if you're talking about the circle in this situation, you're talking about the circumscribed item. If you're talking about the polygon, you're talking about the inscribed item. So, I mean, it's a little bit in the language to be able to make the distinction. Circumference probably is a good related word that should categorize that we're talking about the circle outside of it. If we're talking about which one's circumscribed versus inscribed, it's inside, inscribed, if we're talking about the polygon. Okay, now here is a theorem. If a quadrilateral is inscribed in a circle, the opposite angles are supplementary. Okay, so this is, we're going to use the same figure once again. Here is circle cube with inscribed quadrilateral A, B, C, D. And so what we get to say is that the opposite angles, in this case A and C, if we were to add together their measures, they would be 180 degrees. That's the definition of supplementary. And the same is true for the measures of angles B and D. Okay, great. So we're going to use this one a little bit later on for sure. Now, if you want to have a polygon on the outside, circle on the inside, then you would have a polygon circumscribed about a circle, and it would look something like this. So I believe you have triangle XYZ on your page. So I would like you as a challenge, you don't have to do this, you're not turning it in for any credit or anything, but try your best to figure out where the center of your compass would go. Like, use your compass and try and draw the circle that is inscribed inside the polygon here, okay? And so if you're wondering where the center should be, it should probably be right about there-ish. So let me move forward. Yep, right about here would be good. And so notice that this circle is exactly, it's like fitting inside of triangle XYZ, and that's as big as the circle can be. Because if you make it any bigger, then, you know, the edges are going to pop right out of that circle. So, and notice that there are 3 points of contact, and here they are, A, B, and C, right? And so this is going to be your polygon circumscribed about the circle, and however many edges your polygon has, that's how many points of contact that you're going to have with the circle. Okay, cool. So there you go. A little challenge for you, like figure out where the center goes and how big your radius would need to be in order to draw the circle that's inscribed in this polygon, this triangle XYZ. Anyway, not necessary, but could be a fun little activity for you. All right. Next theorem. The measure of an angle formed by two chords that intersect within a circle is 1/2 the sum of the two measures of the arcs intercepted by the circle and its vertical angle. Oh Lord, what is even being said by this? Okay, so there's a lot that's being described here, but we can simplify it quite a bit by using some colors. Okay, so here we go. Now, when we're talking about the measures of the arcs intersected by the angle and its vertical angle, so we're talking about these two angles right here. Now, obviously this angle, whatever that's measure is going to be the same as this one, right? But notice the relative sizes of the measures of the intercepted arc. And that's because this point of intersection is not at the center. So if it's anywhere other than the center, then we've got to come up with some other way to be able to measure the angle that's being described here, okay? And we could do that by taking basically the average of the two intercepted arcs measures. So we add them together, and then we divide by 2. When we do this outside of the circle, if I'm like, it's coming up in just a moment, we're actually going to take the difference. It's going to look really the same, similar as to what we have here in this formula, but I believe the operation is going to change in between. Okay, but that's a discussion for another time. So this, let me just read the theorem one more time, having the benefit of this figure here. The measure of an angle formed by two chords that intersect within a circle. So these are the two chords that intersect within the circle, chords AD and BC. Okay, so if we want to find the measure of the angle that's formed here, so I'm talking about angle either AEB or CED. Those are the angles we're talking about. Then we have to take 1/2 of the sum of the two measures of the arcs intersected by the angle and its vertical angle. So here's the angle in question, angle AEB, and its vertical angle is angle CED. So we have to take half of the sum of the arcs that are intercepted by those two angles. Again, the two angles are the angle in question and its vertical counterpart. Okay, cool. So that's the formula that goes with that. Here is a different scenario actually this one doesn't have a formula associated with it, I don't think. Let's read it together. The radius or any other line through the center of a circle drawn to the tangent at the point of tangency is perpendicular to the tangent at that point. So the point of this theorem is just to say that the radius here in regard to this tangent line L is perpendicular. Okay, so a right angle is formed. You can put a little box in there and you can make this statement right here. Okay, great. Moving on. This one is going to require a formula to be presented. So let's read the scenario here, take into account the corresponding example figure, and then we'll have an idea of how to write this formula. The measure of an angle formed by a tangent and a chord drawn to the point of tangency is 1/2 the measure of the intercepted arc. So here are the elements that we need here, lit up in red. It's the intercepted arc, okay? That's associated with the angle. So if we want to find a measure of angle ABC, so that's a chord and a tangent line, okay? So the measure of the angle formed by the chord and the tangent line is just half of the measure of the intercepted arc. In this case, that's arc AB, okay? Now, next scenario here, the measure of an angle formed when two secants intersect at a point. Oh, just a moment, guys. Discard the annotations. Oh boy. Just a moment. Pressing pause. Everybody. All right, so we're joined by my daughter, Willow, but she promises she's just going to sit next to me and draw pictures, okay? So where were we? I believe we were trying to illustrate Theorem 925 on the screen here, in which we have the measure that's formed when two secants intersect at a point outside the circle. So we're talking about this angle right here, angle E is what you could call it. It's 1/2 of the difference of the measure of the two intercepted arcs. So which elements do we need here? Well, here's the angle in question, measure of angle E that we're trying to calculate, and it's going to be 1/2 of the difference of the intercepted arcs. Now, so you avoid making any negative angle calculations here, you'll always want to take it in the order of the larger intercepted arc minus the smaller one, okay? The practical reasons for that I think are fairly obvious. We could talk about that more in class if we need to, though. Okay, moving on. Now here's a different scenario in which we have a secant line and a tangent line forming an exterior angle. And so how do we account for that? We will, just a moment. There we go. Sorry, a little distraction there. We will take the following elements here. Okay, so we need to take again, the difference of the intercepted arcs, but the intercepted arcs look a little bit different than in the previous example, in which always you'll want to take the larger of the two intercepted arcs and subtract off the smaller, and then take half of that, and then you'll get the measure of this exterior angle D. Okay, next, what if your exterior angle is the result of two tangent lines that are meeting? Well, in that case, these are your two intercepted arcs. And you'll, of course, it has the same structure algebraically, where you'll take half the difference of the intercepted arcs, and this is how it'll look in that instance. So there were three different instances of taking half the difference for measuring an exterior angle. Now either it's two secant lines, a secant and a tangent, as you see here, or two tangents, as you see in this theorem 9.2.7. Okay, so here we have an even incredibly different scenario here. If we have two parallel lines, intersect a circle, the intercepted arcs between them are congruent. So let's assume that lines AB and CD in this particular figure, that they're intersecting with circle O, and they're parallel to each other. So that means that the measures of the intercepted arcs are equal to each other and therefore congruent. Okay. Now, now that we're done presenting, I think, all of the theorems, we have at our disposal, I just copied this straight out of the book, it's table 9.1. I thought that this was a very interesting and helpful overview of when to use what formula in order to measure a certain described arc. So definitely take a moment to review this table and use it at your disposal as you see fit when you are going through examples. Speaking of which, let's go ahead and entertain a few together as a class. And of course, I took these straight out of your book as well. And this one is a 5-parter. So we have to find the measures of angles 1 through 5 as positioned into this figure right here, using only the figure and given that the measure of arc DC, now that's going to be this minor arc right here, is 30 degrees, and that arc DABC, that's the major arc, on the outer edge of minor arc DC, is trisected at points A and B. Do we remember what the word trisect means? It means that the arc is being cut into 3 equal-sized pieces. So we'll use that along with the configuration of chords and arcs and all of these different things that are happening here, inscribed angles and the like, in order to find all of these different measures. Okay, so let's start off by noting that minor arc DC is 30 degrees, and so that means that arc DABC must be 330 degrees. And if it's being trisected, it's going to give those arcs BA, AB, and BC each an equal measure of 110 degrees. Okay, so hopefully everyone can follow that. That gives us a lot of information right from the get-go. Okay, now we can find the measure of these angles in order, or we could do them in a different order if we see fit. There's no reason why you have to do them in orders A through E alphabetically. But I'm going to go ahead and do them in order. And I'm going to reference the theorem that gives me the ability to make this calculation. So the measure of angle 1 will be half of the measure of arc DC, which was given to me as 30 degrees. So half of 30 degrees is 15 degrees, and this is the theorem that I'm referencing. The angle 2 is another inscribed angle, and it's going to be half of the measure of arc AB, which if you recall down here was 110 degrees. So half of 110 degrees is 55 degrees, referencing the same theorem. The measure of angle 3 is an exterior angle, so we're going to take half of the difference of the two intercepted arcs, AB and DC. So AB was 110 degrees, DC was 30 degrees, subtract them and you will get, what is that, 80 degrees? So half of that will be 40 degrees here. And then I'm referencing this theorem from section 9.2, the 5th theorem in. Measure of angle 4. Angle 4 is an interior angle, so I have to take half of the sum of the intercepted arcs being this 30 degree arc of DC, 100 degree arc of AB, so taking the sum of them, 30 plus 110 would be 140. Half of 140 gives me the 70 here. So I am giving you the setup, right, and referencing the theorem, but I'm not showing you all of the algebra, so we could certainly talk about that more in class if you like. Lastly, the measure of angle 5. Angle 5 is again another interior angle, so we'll do half of the sum of the intercepted arcs, which is going to give you 110 degrees because each of the intercepted arcs are 110 degrees. 110 degrees plus 110 degrees is 220 degrees. Half of that is 110. So I didn't even bother to leave the, the calculation in there, but I am referencing the same theorem that I did to get the measure of angle 4. Okay, cool. Again, more details, let's talk about it in class. Here is another example. We are tasked with finding 3 separate angle measures. We are given that ray AB and AC are tangent. Just a moment, sweetheart.
But Mama, I draw this.
That's great, honey.
And draw some letters.
Okay. So the arcs are tangent to circle O. These rays, AB and AC, are tangent to circle O. And the measure of arc BC, so that's from here to here, is 126 degrees. And that's all we need, believe it or not, to find the measure of angle A, the measure of angle ABC, and the measure of angle ACB. Let's start with the measure of angle A. So notice that it's an exterior angle, and it's the result of two tangents. And regardless of that, we're going to take half of the difference of the intercepted arcs. Now, the intercepted arcs are the BC arc of 126 degrees, but then the major arc for BC is going to be 360 degrees minus the 126 degrees associated with minor arc BC. That's a difference of 234, excuse me. So we take the difference between those intercepted arcs, take half of that, and that's how we get 54 degrees, okay? Now let's talk the measure of angle ABC. ABC, so that's this angle right here. So that'll be half of this intercepted arc. The intercepted arc's measure being 126 degrees, so the half of that will be 63 degrees, and that's via this corollary here. Lastly, the measure of angle ACB, that'll be the same exact calculation because it has the same intercepted arc BC, so we'll take half of that to get the measure of angle ACB as 63 degrees. Okay, let's see. One more example, I think, and then we're done. Or maybe there's another example after this. I forget. Let's go ahead and just tackle this one and see what comes next, if anything. Given we have, of course, this circle, this unnamed circle, there's no center. A measure of angle 1 is 63 degrees. Okay, that's here. The measure of arc RS is some algebraic representation, 3x plus 6. The measure of arc VT is x. So these are the two intercepted arcs in regard to the measure of angle 1, right? So if we want to find the measure of arc RS, we've got to use the fact that the measure of angle 1 is half the sum of the intercepted arcs RS and TV. So here, referencing theorem 9.2.2, in which that is stated, we're going to take half of the algebraic representations that give us the measure of arcs RS and VT. So do a little algebra, combine like terms, take half of it and all that stuff, and we'll get x equals 30 degrees. Well, that's all well and good, but we weren't asked to find x, were we? We were asked to find the measure of arc RS. So put your 30 degrees in right here for x to get the measure of arc RS. 3 times 30 gives you 90. Just a moment, sweetheart. Plus 6, just a moment, is 96 degrees. And so the measure of angle RS is 96 degrees. Okay, there's another example. Let's consider inscribed quadrilateral RSTV, okay, inside of circle O. And we want to ask how are angles R and T related? Well, if you recall from that one theorem, they are supplementary to one another. So that means that they've got to sum their measures to be 180 degrees if you want to use the definition of that term, but ultimately you could just simply state that they're supplementary. Okay, now if the measure of angle R is 112 degrees, then what would be the measure of angle T? Well, it would be the supplementary counterpart, which you can find by subtracting 112 from 180, and you'll get 68 degrees. So therefore, that must be the measure of angle R. Great. Okay, let's complete this partially completed proof, and then we will be done with the video, okay? Just a moment, sweetie. What's up?
I can do the other page.
Just flip the page then, babe.
I can't do it.
Oh, I'll do it. There you go. Fresh page for you.
That's what I need to look.
Oh, okay. There you go. You're all set then. All right, so we're going to complete this partially completed proof. And the first...
Mama,
yes, honey.
after you're done with the headphones, can I have a turn?
Okay, we're almost done, I promise. Let's go ahead and finish this partially completed proof, in which we are given, with this circle, that line segments RS and TQ are parallel to each other, and we want to ultimately prove that arc RT is congruent to arc SQ. Seems legit, but let's go ahead and make sure we get there all the way. So obviously the first statement should be whatever's given, and the reason for that is that it's given. Next, I claim, or the author of this proof rather, claims that angle S and angle T are congruent. And that's because when parallel lines are cut by a transversal, alternate interior angles are congruent. Notice that these are just simply alternate interior angles that were formed when two parallel lines, RS and TQ, were cut by transversal ST. Okay? Then you'll notice the third statement is blank, but it's justified by saying if two angles are congruent, then the angles are equal in measure. So I believe that this congruency statement in statement 2 will be made to be a measures equal statement for those same angles. Okay? Looking at statement 4, it says the measure of angle S is 1/2 the measure of arc RT. That was a theorem that was presented recently that says if the measure of an inscribed angle is 1/2 of the measure of the intercepted arc. And I went ahead and referenced the theorem as well, not that you need to in your proof writing, just to be clear. I say a similar statement for the measure of angle T, and that it's 1/2 of its inscribed angle measure, and so I get to use the same exact justification for that. In fact, I copied and pasted it. If you don't want to write this whole thing out again in your notes, you can just say same as for. That would be perfectly fine. Now notice that in statement 6, I have the right-hand side of equations 4 and 5 set equal to each other, and that's because I directly replace them with what's going on in statement 3. So it's like I do a series of substitutions in order to get there. Notice that statement 7 in its entirety is provided along with its justification, which is to say that I multiplied both sides by 2 in order to get those measures. And then lastly, we're ready to make our proof statement, which is true because two arcs in a circle are equal in measure, then the arcs are congruent to each other. Just a moment, honey. We're almost done. Okay. We're done. Okay. So we brushed a little bit at the end there, but just
you didn't, sir.
Please note that we can always go over things in more detail in class if you like. Okay. Thank you so much for your attention. I'll see you soon.